In the last video lecture of this week, we'll discuss the relation between the Lebesgue integral of an extended Borel function, or a Borel function, defined on an interval of the real line with respect to the Lebesgue measure, the relation between this integral and the good old Riemann integral that we are used to. So this is the main theorem that allows us to say the Lebesgue integral is superior to the Riemann integral. It says if a Borel function on a, let's say, closed bounded interval on the real line, to keep simple, if the Riemann integral of that function is defined, then the Lebesgue integral of that function is also defined, and the value of both integrals will coincide. And how can we prove that? Well, to say that the given function f is Riemann integrable and that its integral on this interval equals a certain value L, a real number L here, it's a real number. It says it is the same as saying for every positive number epsilon, there exist functions g and h such that these are step functions. So step functions here really means here a and b, our function f, and the step function means it's constant by parts. Okay. So this would be the function g, and the function h will also be a step function. Okay. So it is a constant at some short interval, then it changes and remains constant for another interval. So these are two step functions, g and h, such that, of course, g is below f and h is above f, and such that the integral of the step function g on this interval stays close to L. It doesn't go much below L. It stays as close as we want, because this is for every epsilon positive. Well, of course, it will be less than the integral of h, because, well, h is also a step function, which is always above g. So, and this is a very simple to integrate. And, well, it may seem that this definition of integral is circular, but well, actually it is not, because this is just a step function. So we can define the integral for a step function separately, and then after that define the integral for more general functions. And anyway, so what it means for a function to be integrable is that we can find these functions at g and h such that these two inequalities hold. This is what it means for a function f to be Riemann integrable. But now if we think in terms of Lebesgue integral, if we have these functions g and h, since f is between g and h, and we already know the Lebesgue integral is defined for Borel functions and it has a monotone properties, so well, it may be undefined, but it cannot be undefined if you are comparing f with a function h if f is bounded by a function h, and the function h, it has an integral, and then f also has an integral. And likewise, if f is bounded by a function g, which has an integral, and that integral is a number, then f also has an integral. So we can apply monotonicity, and now this is f dm. Let's use here this notation for Lebesgue measure to make it clear we are talking about the Lebesgue integral. So this we have this inequality simply by the monotonicity properties of Lebesgue measure, and we have this equality here because we already know what the Lebesgue integral of a function that takes finitely many values, each one on each different interval, what is the value of that integral. They do coincide for the case of functions which are step functions. Lebesgue measure and Lebesgue integral and Riemann integral coincide there. So these are equal, And since we're assuming the function is Riemann integrable, then for every epsilon, we can find g and h with these properties. So this is larger than L minus epsilon. This is less than L plus epsilon. And since this is true for every epsilon, then the integral, the Lebesgue integral of f on that interval will always also be equal to, let me put here the interval, will also be equal to the same number L, and this is what the theorem was saying. So this concludes the proof of this theorem. Let us quickly point out that the converse is false, and a very good example people like to point out is take the function f, which is the indicator function of the interval 0, 1, excluding rational numbers. So f, it takes values 1 almost everywhere on this interval, but there is still infinitely many points that have in total 0 measure on this interval from 0 to 1. So this is my function f. The function f, it is 0 here, then it is 1 almost everywhere here, but it is also 0 in many places downstairs. So this one is a Riemann, is Lebesgue integrable, and the integral of f with respect to Lebesgue measure, it is simply, since it's an indicator function, it will be the measure of this set, and we know the measure of the set of rational numbers is 0 because it's countable, so this really is just 1, whereas this cannot be Riemann integrated. This function cannot be Riemann integrated because whatever way we find to partition this interval into smaller intervals, in each of these intervals there will be points where the function takes value 0, there will be points where it takes values 1, so the Riemann integral, if we take lower values, it will give 0. If we take upper values, it will always give us 1. So when we partition this interval, if we pick high values, it always gives 1. And these two things are not converging. So this function cannot be integrated with respect to the Riemann notion of integral. And finally, let me mention here what is the corner case of the corner case that we are really not interested in this type of little subtlety in this module. But what if we have a function f that it is defined on an interval a, b, and it is such that it is not Borel measurable? Okay, if we go back to the proposition here, or the theorem here, the theorem, it assumes that the function is a Borel function. It doesn't give any conclusion in case it's not a Borel function. So let us go back here and ask what happens if the function is such that it has an integral, it is Riemann integral, but it's not Borel measurable. Not being Borel measurable, we have not quite defined what its integral would be. Then, well, just out of curiosity, we're not really emphasizing these pathologies and these extreme corner cases here. But in case it's not Borel measurable, then it will still be measurable, FB measurable, where F is some larger sigma algebra. Okay, so it's a function from R to R, and we just need to make the sigma algebra here a little finer than, or a lot finer than the Borel sigma algebra. So it's a larger sigma algebra, larger than B, and it will actually be, we can comfortably take this as the sigma algebra F star that we saw on chapter 2, on chapter 3, when we talked about Carathéodory's lemma. Or when we defined measurable sets. For the outer measure M star. So there's some sigma algebra F star that appeared there at some point, and just so that we know it, it will be measurable with respect to that sigma algebra. So in any case, Riemann integral will not be any better than a Lebesgue integral.